we did in the previous session. So in the previous session, we introduced what are called as inner product spaces, generalizing the dot product which we already know in R2, right? So how we do the dot product, similar properties were there for inner product spaces, right? It's a generalized version, right? And then we saw norm represents the magnitude, right? So magnitude in the sense length of a vector, and the distance between two vectors, how to calculate them using the norm, and some inequalities and equalities we saw based on the properties of norm, right? And what are orthogonal vectors? We saw orthogonal vectors means given two vectors, right? So in the case of dot product, we have seen that two vectors are said to be orthogonal if they are perpendicular to each other. So in that case, their dot product is 0, right? So we have two vectors orthogonal if inner product x comma y equal to 0, then we say that x is orthogonal to y, right? And then what is orthogonal decomposition? So if you have some vector u, right, how can you decompose it as u1 plus u2, where u1 is perpendicular to u2? So this is what is orthogonal decomposition. So we have seen how to do such a decomposition, right? Precisely what is u1 and what is u2. We have seen this in the previous session, and we have seen some inequalities as well, right? The triangle inequality, and what was the other inequality? We saw the parallelogram identity, the triangle inequality, and I guess the other one was. Can anyone remember what was the other inequality? No one remembers. Yes.
Cauchy-Schwarz inequality.
Yeah. What was the other one?
Cauchy-Schwarz inequality.
Exactly. Good. Um, least square fit. So today we are going to look at least square solution. Uh, so today we will be looking at first what is orthonormal basis. So someone has asked about least square fit. Today we are going to look at least square solutions. Okay. So first we will start with orthonormal basis, and if you have any basis, how to convert it into an orthonormal basis using Gram-Schmidt process, right? And then we will see what is orthogonal complement, least square solutions, and projections. So these are the things we are going to see today. All right. Okay. So a quick glance on the properties of inner product. So for symmetry in Rn, we have symmetry, and for Cn, we have what is called as conjugate symmetry. And for Rn, we have linearity in both the arguments. And for Cn, we have linearity in the first argument and conjugate linearity in the second argument. So in the sense, what is conjugate linearity? Can anyone say? If you have u, comma, AV plus BW, what is the property you have for conjugate symmetry?
Inner product of u comma av plus u comma b omega.
So you have A bar in a product of u comma v plus B bar in a product of u comma w. So conjugate symmetry means you have conjugate linear means you have the conjugate for the scalar part, right? So this is for the second argument. For first argument, it is just linear. You don't have any conjugate, right? And then you have the positive definiteness for both Rn and Cn. So that is inner product v comma v is greater or equal to 0 if and it is 0 if and only if the vector is 0, right? Okay. So we know that we say that two vectors are orthogonal if the inner product is 0. Now what is mean by an orthonormal set? Let us say you are given with a set of vectors. When do we say the given set of vectors is orthonormal? Okay, first of all, orthonormal means two things. So orthogonal plus normal, right? First of all, it should be orthogonal. So it means what? Take any two vectors. So any two vectors means I not equal to j. So in that case, inner product vi comma vj equal to 0, and then norm of each of the vector is 1. Okay, so such vectors are said to be orthonormal vectors. All right. Okay. So now suppose you are given a set of vectors v1, v2, vk which are orthogonal. Okay. So how to make them orthonormal? So suppose let us say only the first condition is there. How to make the norms to be 1? Okay, if we divide each of the vector by its norm, then what is the norm of the new vector? So here we have norm of v by norm v. So what is the norm of this vector? So now norm v is a scalar, right? Norm v is a scalar. So I can bring it out of the norm. Already it is a positive number. So when I apply modulus, it will remain the same. So I can simply write 1 by norm v, and then numerator you have norm v. So this is for v non-zero, okay, which is equal to 1. So any vector, if we divide it by its norm, then the norm of this new vector is equal to 1. Okay, so given any orthogonal set of vector, you can orthonormalize it by simply dividing each of the vector by its norm. Is that clear? Okay, fine. Now we have already seen some similar example in the last session. Let's see how many of you can recall it and do it here. Consider the orthogonal vectors 1, 1, 1, minus 1, 0 in R3. Find a third vector in R3 which is orthogonal to both the vectors. How to do this? So we take, let's say this is V1, this is V2, and let the third vector be some x comma y comma z. Right? So now we want V1 comma V3, this inner product to be 0, as well as inner product V2 comma V3 to be 0. Right? We are in R3. So what is the inner product? V1 comma V3. What is the inner product?
X plus Y
X plus Y
plus Z
plus.
equals to 0.
Very good. What about the second one?
Minus X plus Y equals to 0.
Okay, so now here you have two equations. So you, from this you have minus x plus y will give you x is equal to y. So now substitute this back here. So if we substitute it here, then what will we get? 2x plus z is equal to 0, which implies z is equal to minus 2x. Right? So how can we write this V3? So what are the vectors? So the set of all vectors orthogonal to V1 and V2 are, how can we write? So let's say x comma minus 2x, x is in R. Is that fine? Yeah. So can you pick a basis element for this?
1, 1 minus 2.
Yes. So you can have it as span of 1, 1 minus 2. Okay, fine. Now we are having, so let's now call this vector as V3. Okay, so let's take one specific vector. So this is the answer. So here let's see. So we have V1, V2, V3. Now how to norm, so first of all, are they all orthogonal? We have already V1 in a product V3 is 0, V2 in a product V3 is 0. What about V1 in a product V2? That's also 0.
That's also 0, yeah.
So this is an orthogonal set already, right? So already we know that V1, V2, V3 are is an orthogonal set, right? This is an orthogonal set. How can you make them orthonormal? Orthonormal means you need the second condition.
So
How can
norm
you?
should be 1, right?
Yeah.
Norm should be 1.
Yes. How can you convert them into a vector with norm 1? So if this is orthogonal, what we know, if we divide by their norms, then it will become Orthonormal.
Normal.
Okay. So what is norm of this vector?
Under
Norm of,
root 3.
yeah. So this is root 3. Okay. So if you take the vector, let's say u1 is equal to 1 by root 3 v1. Okay. And what is, so this is norm v1. What is norm v2?
Root 2.
Root 2. What is norm v3?
Root
2.
6.
Okay. So here
Root.
we can have u2 as 1 by root 2 v2 and u3 is 1 by root 6 v3. So now u1, u2, u3 is an orthonormal set. Okay. So you understand what's the difference between orthogonal and orthonormal? Okay. Which one implies the other one? Can every orthogonal set be an orthonormal set?
No.
No. What about the other way around? Is every orthonormal set an orthogonal set?
Yes.
Yes. Okay. Okay, fine. So I guess now you have a clear idea of what is an orthogonal set and what is an orthonormal set and how to convert an orthogonal set into an orthonormal set. Okay, fine. So the next thing is that we have already seen. So in the case of R2, in the case of what R2, what did we see? So suppose let us say in we are in R2. Okay, so if we are in R2 and then you have some vector, so let us say you are having some line here passing through origin. So let's try to draw through the origin. So you have some line through origin, okay, and you have something orthogonal to it, okay, some vector orthogonal to it, okay, either along origin or somewhere else also. So now if you have this kind of vectors, are they linearly independent? Let's say you have some vector here and some vector here. Are they linearly independent? When the angle between them is 90, are they linearly independent?
Yes, ma'am.
Yes, ma'am.
Yes. So what do we know? So we know that orthogonality, if two vectors are orthogonal, orthogonal implies
Linearly
linear.
independent.
Angle between them is 90 degree.
Yeah. So that is, see, angle between them is 90 degree. You can visualize only in R2 or maximum in R3. But in general, orthogonality tells us that the vectors are first of all linearly independent. Okay, we know that the inner product is 0 and this implies that the vectors are linearly independent. Here is a simple proof of that. So first, what is the definition of linear independence? So let's say you are having some k vectors v1, v2, vk. So to show that they are linearly independent, how do we show? We say that first of all we assume a1 v1 plus etc ak vk equal to 0, and then if all the ai's are 0, then we know that this given set is linearly independent, right? So now first we have assumed that this is equal to 0, right? What is that we need to prove? Each of the coefficient is 0. Okay. How are we going to prove that? So let us take any vi, okay, and take the inner product with this. So since inner product with a 0 vector is 0, so this is already 0. Why? Because this part is 0. This part is equal to 0. So this inner product is 0. Okay, now we are going to use the linearity in the first argument. Okay, what are we going to use? Linearity in first argument. If we apply linearity in the first argument, then what will happen? You can split them as a1 into inner product v1 vi plus etc ai vi etc. So you can split it in this way. And what do you know? You know that inner product vj comma vi is equal to 0 if, can you say what is the condition if? See, these are
I
all
is not equal to j.
exactly. So if you have I not equal to j, and if I equal to j, then what is the inner product? Can you tell? Because it is given that they are orthonormal.
Then v I should be 0.
No, no, no. I'm asking if
1,
I equal to j, then what is inner product vj comma vi?
1.
Yes, because it is orthonormal, right? Orthonormal means norm is equal to 1, right? But norm is equal to 1 means what? Norm square is equal to 1. It means inner product vi comma vi equal to 1. So this is equivalent to saying, inner product vi comma vi is equal to 1. Both are equivalent. Okay, so here inner product, this only this term will be 1, and the all other terms will become 0, right? So these terms are becoming 0 and only this is 1, so this coefficient alone remains, right? So we have taken any vi and then we got the answer ai as 0. So this means what? For all I, ai is equal to 0, and hence v1 v2 vk are linearly independent. Is this proof clear for everyone? Yeah, you need to
Yes, ma'am.
respond. Okay, good. Okay, fine. So here, some again we are having some inequality similar to what we have seen in the previous session. In the previous session, we have seen how to apply Pythagorean theorem, right? So if we, what do we know from Pythagorean theorem? So if you have two vectors u and v perpendicular to each other, what is norm of u plus v whole square? Norm
Hypotenuse.
u square plus norm v square, right? So this is what we already know, right? So we also saw it from the picture of a right angle triangle, right? So suppose this is u, then this is v, so this distance is norm u square and this is norm v square, and so this is norm of u plus v whole square, right? Okay, so now what is that here we are having? If v1 v2 vk are orthonormal, then norm of a1 v1 plus etc ak vk whole square is equal to mod a1 square plus etc mod ak square. It's kind of a generalization of this. Okay, generalization of the Pythagorean theorem. Okay, here is a simple proof based on the Pythagorean theorem. So either you can use induction and prove it, or you can use Pythagorean theorem. Any way you can prove. Okay, but I don't know how many of you know induction, so I have just used Pythagorean theorem to show a simple proof here. So here first we have a1 v1 plus a2 v2 plus etc ak vk, right? And given v1 v2 vk are orthonormal, can we say that a1 v1 is orthogonal to a2 v2 plus etc ak vk? First of all, is this true? So can we simply see this a1 v1 in a product a2 v2 plus etc ak vk? What is this? So this is a1, so a1 in a product v1 v2 or a1 a2 bar, right? So you have a1 a2 bar in a product v1 v2 plus a1 a3 bar in a product v1 v3 plus and so on up to a1 ak bar in a product v1 vk, right? Now what are these inner products? What do you know about these inner products? You know that each of them is equal to 0, right? So this means the entire inner product is equal to 0. So these two are first of all orthogonal, right? These two are first of all orthogonal. So if they are orthogonal, we can apply Pythagorean theorem. So if we apply Pythagorean theorem, so this is your u, this is your v, so you can split it in this way. So the first step, is it clear?
Yes,
Yes?
ma'am.
Okay. So from this, next what we can do, We have now splitted this part. Same way, can we keep on applying the same things? Let's say first we take A2, V2 and the remaining part. Now we know that again from similar calculation.
Ma'am, why you are taking that conjugate? Is it in complex?
We are talking about general Fn, so we need to take conjugate. If it is real, then the conjugate is going to be simply A2 itself. So it's better to take the conjugate because here we are talking about the general scenario. So we are talking about Fn. So it's
Okay.
better to put conjugate. Okay, fine. So again the same thing will happen. Again you see that these two are again orthogonal. So again you can apply Pythagorean theorem and you can split it further and you can keep on splitting till you have the entire answer like this. Okay, first of all, note one thing, that here this is equal to what is norm of A1 V1 square? Mod A1 into norm V1 square plus norm A2 V2 plus etc. AK VK square. But what is norm V1 square? Given it is an orthonormal set. So what is norm V1 square?
Norm V1.
1.
1, right? So here you will, sorry, here square I missed. So here you will simply have mod A1 square and the remaining term. So in each step you will get mod A1 square and then mod A2 square and so on. Then till mod AK square you will get. So how are we doing this? Is the idea clear for everyone? We are simply going to repeat the Pythagorean theorems for each step till we get the entire term. Is that clear?
Yes, ma'am.
Good. Okay. So now what is an orthonormal basis? Okay, what is an orthonormal basis? Okay, so we already know what is a basis. Can anyone tell what is a basis?
Spanning set, linearly independent.
Yes, a set which spans and also is linearly independent, that is a basis. Okay, now what is an orthonormal basis? An orthonormal set which also satisfies the conditions of a basis. So it means what? So already we know that orthonormal means it implies linearly independent. So what is the other condition we need? We need the spanning condition. That's all. Right? So a basis V1, V2, Vn of Fn is said to be orthonormal basis if the vectors V1, V2, Vn are orthonormal. Okay. Any basis you take, if the vectors are orthonormal, then that is an orthonormal basis. Okay. So if V1, V2, Vn in Fn are orthonormal, what do you know? If they are orthonormal, do you know that they are already linearly independent? Yeah. So if V1, V2, Vn are orthonormal,
Means they are linearly independent.
yes, you know that they are linearly independent. And also, if so, you have n linearly independent vectors in Fn. So do they span Fn? N linearly independent vectors.
Yes, ma'am.
So you see that they are linearly independent and it spans Fn. So it forms a basis. So any n vectors in Fn which are orthonormal will form an orthonormal basis. Okay. So already we saw this example. So in this case, what were the orthonormal vectors? So they were, so 1 by root 3, 1 comma 1 comma 1, 1 by root 2. So u1 is equal to this, u2 is equal to 1 by root 2 minus 1 comma 1 comma 0, and u3 equal to 1 by root 6, 1 comma 1 comma minus 2. Right? So these three are orthonormal in R3. So do they form an orthonormal basis now? We have three vectors in R3 which is orthonormal. So this is an orthonormal set. So do they form an orthonormal basis? Yes or no?
Yes, ma'am.
Yes, right? So this forms an orthonormal basis. Right? So the answer is yes. So they form an orthonormal basis. Good. Okay. Now what is the advantage of having an orthonormal basis? What was the use of a basis? So basis helps us to represent the entire vector space with very smaller set, right? So only if with the vector smaller basis we can represent any given vector in the whole vector space. It is a representation. So we already have a representation. Then why we need this orthonormal basis and all? What's the advantage of it? Okay, fine. So let me give a small let me ask a small question. Let me see how many of you can tell. So let's say you are having something like this: 1 comma minus 2 and 2 comma 3. Are they linearly independent?
Yes, ma'am. Linearly independent.
So they are linearly independent. So do they form a basis for R2?
Yes, ma'am.
Yes, ma'am.
So this is a basis for R2. All right. Okay. So now let us say I have some vector x comma y, or specifically maybe I have, let's say, 7 comma 9. How can I, so since it is a basis, I know that I can express it as a linear combination of these two vectors, 1 comma minus 2 and 2 comma 3. How do I find what is A and what is B?
We have
Dot
to equate
product
them.
with 7 comma 9.
So we need to solve the system of linear equations, right? We need to solve the system of linear equations to find the answer, right? So we need to solve this. So this is in the case of R2. For R3, R4, so the complexity will get more, right? So we need to solve the system of linear equation to find what are the coefficients. But if it is an orthonormal basis, the process of finding the coefficient is much simpler when compared to a regular basis. How is it simpler? Let's see. Okay, so let v1, v2, vn be an orthonormal basis of fn. Then the coordinates of v in fn are given by this. How are the coordinates inner product of v comma v1, v comma v2, etc., v comma vn? Okay, so first of all, this is the basis. So if this is a basis, any vector can be expressed as a linear combination of v1, v2, vn. So we have written v as a linear combination of the basis elements. Now let us consider what is inner product of v comma vi. What is inner product of v comma vi? Inner product is x1 times of, so this is now, so x1, x2, xn are scalars. Okay, so here x1, x2, xn, these are all scalars, right? So these scalars come out, and so you simply have inner product v1, vi, and so on, and you know that, so these terms will become 0, and only this is 1, because it is an orthonormal set. v1, v2 is orthonormal, so everything all the inner products will become 0 except this term. So you are left with xi. So what is the coefficient xi? It is simply inner product v comma vi. Okay, so now do you understand what is the advantage of having an orthonormal basis? See, here let us say you are in R2 or R3. So even in this case itself, okay, so in this case itself, you are already having an orthonormal basis. So now for this orthonormal basis, given any vector, how can you express them as a linear combination of these vectors? Let us say, let's try. So let us try, maybe can you write, let us say 2 comma 3 comma 5 as a linear combination of a1, u1, a2, u2, u1, u2 and u3. What are the coefficients? How do you compute? A1 is simply inner product 2, 3, 5, comma 1 by root 3, 1 comma 1 comma 1. What is the answer? 1 by root 3, 2 plus 3 plus 5. So it's simply 10 by root 3. Similarly, what is A2? Now can you calculate what is A2? Tell me the value of A2 quickly. For A2, inner product of this vector, let's say this is some u, inner product u comma u2. What's the answer?
1 by root 2.
Yes. And then minus 2 plus 3, which is just 1 by root 2. Correct? What is A3? 2 plus 3 minus 10. So you have minus 5 by root 6. So you see that we computed the coefficients so easily. We did not have to solve any system of linear equation. We found what are the coefficients very easily. Right? Now you can see what's the advantage, right? Yes or no? Yeah. Now here is a simple exercise for you all. So this is just like standard basis is something very commonly known. Hadamard basis is also something very so used in many places. Okay, Hadamard basis. Okay, so now so this is a basis for R3. Okay, and you can check that this is an orthonormal basis in fact. Okay, this is an orthonormal basis. What is the norm of this vector? You can verify that it is 1. Each of the norm is 1. Okay, so this is an orthonormal basis and their inner products are 0. So this is an orthonormal basis. Can you quickly find the coordinates of the vector 1, 2, 3, 4 with respect to the Hadamard basis? Everyone do this and tell me the coefficients quickly. So let's say this vector is u, or since all are given as v, so let me call it v. So can we write v as a1 v1 plus a2 v2 plus a3 v3 plus a4 v4? Everyone calculate what are the AIs and tell me the answer.
A1 equal to 5,
Okay.
A2 equal to minus 1, A3
Okay.
equal to minus 2, A4 equal to 0.
How many of you got this answer? Raise your hands. Let me see if Nanda got. Who gave the answer? Sorry, I did not notice who gave the answer. Sanand, take your time. Okay, sure. Okay, good. Sanand, you understand the concept, right?
No, ma'am.
What you did not understand? See, it's very simple. What we are doing here for finding A1, it is simply inner product of V comma V1. That's all. Right? So what is V here? This is the vector V. So it is 1 comma 2 comma 3 comma 4 comma V1. So 1 by 2, 1 1 1. Okay, so what is that? 1 by 2 is just a number, so we are in R3, so here it is just linear, so we can bring the 1 by 2 outside, and then we are going to do the inner product. So 1 into 1 is 1, 2 into 1 is 2, 3 into 1 is 3, 4 into 1 is 4. Okay, so what is that you are getting? You are getting 3 plus 3, 6 plus 4, 10, so 10 by 2, which is 5. Now do you understand?
Yes, ma'am, understood.
Okay, so same way you have to calculate A2, A3, A4. So in place of A2 means you have inner product V comma V2, V comma V3, V comma V4. Okay, fine. How come it is? Okay, sorry. Thank you. It is in R4. Sorry. Thank you for pointing out. All right. Okay, fine. All right. So what is the next thing, so we know that if you have an orthogonal set, so let's say you have an orthogonal set, then you know how to convert it to orthonormal set. You simply divide by its norm. But if you don't have an orthogonal set, but you simply have any basis, okay, you just have some basis, how can you convert it into an orthogonal basis? Okay, so you have any vector space, any subspace, and you have some basis, and then how can you form a orthogonal basis from the given basis? For that, we have what is called as the Gram-Schmidt orthonormalization. Okay, so let us say you have a set of vectors v1, v2, vk. Okay, these are linearly independent vectors. Okay, so this S is equal to, so let's say the span of v1, v2, vk. So now let's say that this, we call it as some S, and we know that this S is a subspace. Okay, and these are the bases for that subspace, basis of S. Right? Why? Because they are linearly independent and they span this subspace S. We know that it is a basis. Now, how can we convert this v1, v2, vk into an orthonormal set of vectors? Okay, so here is the formula. So here you have this formula. u1 equal to v1 by norm v1, and in general for any wj, what is wj? Is vj minus, so you have to first, this is the first orthogonalization, and then wj divided by norm j will give you the orthonormal vector. So if you have to, if you have, can remember this formula only, you can do the Gram-Schmidt orthonormalization. Okay, so this formula is based on what is called projection, but I don't think that the theory part is deeply covered here. So just you can go through this formula and try to remember this formula, but you can also remember that it is based on projection. Those who are interested to go behind and look the theory, like how this works, how you got this thing, there are several lectures, I guess. You can go and check that. Okay, so how projection is related to this, maybe I can also send some links if anyone is interested. Okay, fine. Okay, so now we'll do some problem to understand the application of the Gram-Schmidt process. So here you are having some set of vectors. First of all, can you all tell me how to determine whether this given set of vectors are linearly independent or not?
Find the determinant.
Yes, so can you quickly
Determinant
compute the
should not
determinant
be-
and tell me? Quickly compute the determinant and tell me what's the answer. Okay, Shonali, I will give you the link. Yeah, determinant is non-zero. How many of you can figure out that the determinant is non-zero? So let's call them as initial
It
vectors.
is 3.
Okay, so it is anyway non-zero. Good. So determinant of v1, v2, v3 is non-zero. This tells you that v1, v2, v3 forms a linearly independent set and hence a basis for R3. Okay, so how do you convert them to a orthonormal set? Okay, the first step is u1 equal to v1 by norm v1. So can you compute and tell me what is u1? There is nothing much to compute. u1 is v1 by norm v1. What is norm v1?
Root 3.
1 by root 3. 1 comma 1 comma 1 is your u1. Okay, so now what is the formula for computing the next vector? So for that, let's apply this. Okay, so how are we going to apply? So maybe we'll write for two vectors here so that it's easier for us to do. So what is w2? It is V2 minus inner product V2 comma U1 into U1. Okay, so it stops with U1. So for V2, W2 only this much. And what is W3? V3 minus inner product of V3 comma U2 into U2 minus inner product V3 comma U1 into U1. Okay, so these are the two formula which we are going to use now. So can you use both this formula here and compute what is W2 and W3? Everyone do it. Write down these formulas for W2 and W3, compute and tell me the answer. W2 equal to V2 minus inner product V2 comma U1 into U1. So first you need to compute what is inner product V2 comma U1. What is inner product of V2 comma U1? So it's 2 by root 3. Am I correct? So we can apply it here. 1, 0, 1 minus 2 by root 3 U1. And U1 there is another 1 by root 3. So 1 comma 1 comma 1. So you get 1 comma 0 comma 1 minus 2 by 3 into 1 comma 1 comma 1. 2 by 3 into 1 comma 1 comma 1. So you have 1 minus 2 by 3. So 1 by 3. And then minus 2 by 3 and 1 by 3. Is this correct? Did I do any calculation error or is it correct?
Is there any alternative method?
No. This is the only method. And at least to my knowledge, this is the one we have always used. What is the norm of W2? Compute the norm of W2 and tell me. What is norm W2?
Root 6 by 3.
Root 6 by 3. Okay, good. Okay, now we have to apply the next formula. So next formula is W3 equal to V3 minus inner product V3 comma U2 U2 minus inner product V3 comma U1 U1. Right? So first compute what is inner product V3 comma U2 and then compute V3 comma here V3 comma U2 and then U1. Compute these and tell me the answer.
0, 1.
Sorry, what?
Sorry, ma'am. Inner product of V3 into U2. So what is your U2? Where U2 I did not write what is U2. U2 is equal to root 6 by 3 into 1 by 3 times of W2. So here you have this. So you have root 6 by 9 1 comma minus 2 comma 1, or you can again rewrite it as
Did I do any mistake? I'm doing it correctly, right? Root 6 by 3. Oh, I have to divide. So it's the other way around. I can write one more step for clarity. U2 equal to W2 by norm W2. So this is W2 and this is 1 by norm W2. So this is 1 by root 6 of this. So this is your U2. What is inner product of V3 with U2? So the first entry is 0 and then you have minus 2 minus 1. What's the answer? What is inner product V3 comma U2?
Zero comma minus 2 by root 6 comma minus 1 by root 6.
Sorry, the inner product is just a scalar, right? What's the scalar value?
Minus 3 by root 12.
Minus 3 by root 12. Okay, but in V3 in inner product U3 1 by root 6 is there. Why it became 12?
Minus 2
Minus
upon
1
root
by
6.
root 6.
Root 2 into root 6, root 12.
Where is root 2? So it's just V3 inner product U2, right? Where is root 2 here? See, in the formula,
Minus 2 upon root 6, is it?
minus 3 by root 6, yes. Okay. What about inner product V3 comma U1?
2 by
U1
root
is
3.
there. So you have it's 0, I guess, right? V3 in a product U1 is 0, right?
Yes, ma'am.
Yeah. So this part is 0. Okay. So now this part is becoming 0. So only you have this. Now let's write 0 comma 1 comma minus 1 minus minus into minus will become plus 3 by root 6 into U2. What is U2? U2 is again you have 1 by root 6, 1 comma minus 2 comma 1. So you have to simplify further. So this will become 6. So 1 by 2 times of 1 comma minus 2 comma 1. What's the final answer? You have 1 by 2 comma 1 comma 0 comma minus 1. Is that correct?
Yes, ma'am.
Okay. So now what is U3? W3 by norm W3. Compute norm W3. Tell me the answer of norm W3.
Root 2 by 2.
Yes. Root 2 by 2. So here you have 2 by root 2 into again W3. So 1 by 2, 1 0 minus 1. So you have 1 by root 2, 1 0 minus 1. So what is the final set of answers you are having? U1 equal to 1 by root 3, 1 comma 1 comma 1. U2 equal to, what was the U2? 1 by root 6, 1 comma minus 2 comma 1.
and u3 equal to 1 by root 2, 1 comma 0 comma minus 1. You can also verify that each of their norm is 1 and inner product ui uj is 0. So what do we know? Ui uj is equal to 0 if I not equal to j and is equal to 1 if I equal to j. You can verify this. Straight away you can verify. This first one is very straightforward. 1 minus 2 plus 1, 0. Similarly 1, 0 minus 1, 0. Here also 1 minus 1, 0. So you can obviously see that it is orthonormal, and also you can check the norms. The norms must be 1. Yeah, fine. So the applying Gram-Schmidt process, is it clear for everyone?
Yes, ma'am.
Clear, ma'am.
Good. Okay. So for every subspace of Fn, there exists an orthonormal basis. What's the logic behind it? For every subspace, there is a basis. If there is a basis, you know how to convert into an orthonormal basis. And hence, you know that every subspace of Fn has an orthonormal basis. Right? Okay. So the same thing for this also. For any operator T from Cn to Cn, there exists an orthonormal basis with respect to which the matrix of T is upper triangular. Right? So I guess it was in week 8 or week 9. I'm not sure whether the triangularization part. Okay, it was in either week 9, 8 or 9. So we have seen that suppose there are few matrices which are not diagonalizable, right? All matrices need not be diagonalizable. So in that case, what we saw, we can triangularize any matrix. That is true for any matrix, right? So in that case, we have a basis with respect to which a matrix is triangular, right? So in that case, you have a basis with respect to which the matrix is triangular. You take that basis and apply Gram-Schmidt. Then you will have an orthonormal basis with respect to which the matrix is upper triangular. Okay, so these are some things to know. So here is the other part. Okay, so what is orthogonal complement? Before looking at the definition, we will go back to an example to have an understanding of that what idea here. Okay, so here we had two vectors. Okay, v1 and v2. Okay, how many of you remember what is how to write the span of v1 v2? What is span of
AV1 plus BV2.
Very good. So it is set of all AV1 plus BV2. So now this is a subspace of R3, right? So this is a subspace of R3. So any vector here is of the form A minus B, comma A plus B, comma A comma B in R, right? So this is your, let's say this is your S. Okay, so we already saw that all the vectors orthogonal to v1 and v2 is given here. So this, now let us take any two vectors from here, one vector from here and one vector from here, and we will see what is happening. Okay, so let's take one vector from S. Okay, so A minus B comma A plus B comma A. Okay, and then we will take one vector from here, x comma minus 2x. What is the inner product? Ax minus bx comma ax plus bx comma minus 2ax, right? So now you see that, so not comma where it's plus, sorry. Bx and then plus. So here you can see that you can cancel out this, right? And you are left with 2ax minus 2ax, which is 0. So what you can see, any vector here is orthogonal to any vector here, right? So any vector here is orthogonal to any vector here, and this set you call it the orthogonal complement of S.
Okay, this is the orthogonal complement of S. Okay, so if I have space somewhere else, I want to also show it in R2. Okay, in R2, let us say you have, let us say your S is span of 1, 1. Okay, so span of 1, 1 is, so let's say this is 1, 1. Then you know that the line passing through is 1, 1 is S. So this is your S. Right? Now, can you give an vector which is orthogonal to 1, 1? Any vector which is orthogonal to 1, 1.
1 comma minus 1.
Yes. So let's consider 1, minus 1. So you have 1 and minus 1. Okay, so it's here. Okay, so let's consider the span of one comma minus 1. The span of 1 comma minus 1 is simply the line which is passing through 1 comma minus 1 in origin, right? So it's this line. What you can immediately observe, you can observe that they are orthogonal. So you take S and any vector orthogonal to this, and S perp is 1 comma minus 1. Okay. So there is something more I want to show. I have to switch screen for that. 1 minute. Okay. So this GeoGebra page is visible for you?
Yes, ma'am.
Okay. So in this GeoGebra page, I have just taken some random plane here. So here it is this plane here. You see this blue color. This is the x equal to y equal to z plane. Okay. So now you see this plane, and what is, I have taken a vector which is orthogonal to vectors in this plane. Okay. So for example, 1 comma 1 comma 1. Any vector 1 comma 1 comma 1, okay, is take any vector from this plane, then 1 comma 1 comma 1 is orthogonal to this particular plane. Can you see that? If I take the cross section, this is the kind of the plane, and this is the span of 1 comma 1 comma 1. Can you see that they are orthogonal? Right, the
Yes,
plane
ma'am.
and the line. Okay, so this is kind of, you can see the perpendicularity, right? It is kind of going straight perpendicularly. Okay, fine, you understand, right? All right. So coming back here, so what do we see? So here we see that for a line in R2, we can find a line, another line which is orthogonal to this line, right? And here what we saw, so here, what is the dimension of this particular, where was the example? Yeah, what is the dimension of this S? Can you say? What is dimension of S?
2.
2. Okay, so because you have two vectors in the span of S, two vectors need for spanning this set S. And what about the dimension of S perp?
2.
Come on, how many vectors are there in the spanning set?
3. 3.
1.
1, right? So you can always see that. So here S is a subspace of which space? S is a subspace of, hold on Sanand,
R3.
R3, right? S is a subspace of R3. If S is a subspace of R3, what do we know? Dimension of S plus dimension of S perp. Do we get it equal to 3? Yeah, so 2 plus 1. Same way, do we get the similar thing here as well? So here in the case of lines in R2, what is the dimension of S?
1.
So dimension of S perp again
1.
1. So we see the dimension of S plus dimension of S perp is equal to dimension of R2, right? So S is a subspace of R2. So we see that this is equal to 2. Okay, so in general, you take any subspace S of Rn. Okay, can you tell me how to find the dimension of S perp without even knowing what is S perp? It should be,
N minus dimension of S.
that's all. Okay, so you have now a basic understanding of what is an subspace and the orthogonal complement of a subspace. Do you have an understanding of what are they? Yeah, yes or no?
Ma'am, what is that perpendicular S?
See, this is the set of all vectors. So let's take any vector in S. Okay, S perp is the set of all vectors which are all orthogonal to all the vectors in the set S. Okay, just like I showed you here, just like I showed you in this example. So you take any vector in S, okay, and any vector in S perp. So any vector here is perpendicular to any vector in this set. So in that case, this set is the set of all orthogonal vectors orthogonal to the vectors in S. Okay, so here is the formal definition if you want more clarity. So the orthogonal complement of a subspace denoted by S perp is a set of all vectors which are orthogonal to all vectors in S. Okay, it should be you collect all the vectors which are orthogonal to every single vector in S, that is the S complement or S perpendicular. Now do you understand, Sanan? What is this S perp?
Yes, ma'am. Thank you, ma'am.
Okay, good. So the formal definition is this. So S perp is set of all U in Fn such that inner product U comma V equal to 0 for all W in S. Okay, you collect all the U which are orthogonal to all the elements in S. That is your orthogonal complement. Okay, fine. All right. Okay, so we have seen what is how to find the orthonormal basis of a subspace and then orthogonal complement of a subspace. So orthogonal basis, orthonormal basis, we saw what is the advantage of having an orthonormal basis. We know that if we have an orthonormal basis, then any vector can be easily represented in terms of an orthonormal basis, right? Okay, now what is the advantage or what is the purpose of having an orthogonal complement? Okay, so before looking at the answer for this, so let's look at some properties of this orthogonal complement. So for any subspace, yes, the orthogonal complement is also a subspace. Okay, so what is the condition you usually check for a subspace? Can anyone remember? So for a subspace, what are the conditions we check? You take any two vectors u1, u2, a u1 plus b u2 should also be in the same space, then it is a subspace. So in that way, so we are taking any two vectors in this set. Okay, and we want to show that a u1 plus b u2 also belongs to the set. Okay, so in a product a u1 plus b u2, we are going to, if we want to say that it is in this set, then we want to say that it satisfies this condition. What is the condition? AU1 plus BU2 in a product W with W should be 0 for any W. So we are taking a random W in S and we are going to do the inner product. But since already U1 and U2 are in S perp, they already satisfy the condition. So inner product U1W is 0, inner product U2W is 0, and hence the entire inner product is 0. So we have AU1 plus BU2 in S perp. So S perp is a subspace. Is this clear for everyone that S perp is a subspace? Yeah. Okay. So, and then what can be there in the intersection of S and S perp? Already we have seen in the case also. What is there in the intersection of these two, S and S perp? What is there? Only origin. So
Origin.
also in the visualization which I showed in GeoGebra visualization, What was there in the intersection of the plane and the orthogonal line which is passing through?
It is
Again,
origin.
origin, right? So S intersection S perp is always just singleton 0. Okay, so you can see that if you take a vector u here, you take any vector u here, u in S intersection S perp, which is in both, then what do you know? Inner product u comma u is 0, but we know that this is possible only when u is equal to 0, right? So in that case, any vector here is just a 0 vector is there. There is no other vector apart from 0. So these are two main properties about the S perp, and also the dimension property I have already told you. Dimension of S perp is n minus k. This also we have seen. Oh, this is another thing. This is something you know from the basics of orthogonality, right? So suppose you have some line, right? And you have another perpendicular line. So what is the line perpendicular to the perpendicular line? Again, the original line, right? So complement of complement is again yes. So this is perpendicular to this. And what is perpendicular to this? Again, the same line, right? So S perp is S. This part is also clear, right? Complement of complement is S. Okay, is this clear? Okay, so let's try out few examples to see whether you really understood what is orthogonal complement. Okay, okay, so let's look at the first example here. Y is equal to 3x. Can anyone figure out a basis for y equal to 3x?
1, 3.
1, 3.
1, 3.
Okay, so you see that. So let's say that w is equal to set of all x comma y such that y is equal to 3x. Okay, now this is the span of 1 comma 3. Okay, now how do you find the orthogonal complement? So for
3,
finding
minus.
yeah, so you take any vector x comma y and find the inner product and take the inner product with 1 comma 3. Equate it to 0. So you get x plus 3y equal to 0. So you have x is equal to minus 3y. Okay, so what is your W perp? W perp is set of all x comma y such that x is equal to minus 3y. Okay, what is the basis here? Any basis?
1, minus 3.
minus 3 comma 1.
Minus 3, 1.
Yes. Okay, minus 3 comma 1. Okay, so you can clearly see that these two are orthogonal. Okay, also what is dimension of W here?
It is 2.
1. 1.
1.
And
Okay.
dimension of W perp is
1.
1, right? And you see the dimension of W plus dimension of W perp is equal to dimension of R2. Okay, fine. Okay, let's look at the second case. The second case, I'm taking y equal to 3x, but now I am in R3. So you have to be very careful. So W equal to set of all x comma y comma z, where y is equal to 3x. So this is set of all x comma 3x comma z. So we know how to find a basis in this case. How to find a basis? Can you remember? You take x, z as coefficients and then try to write the vectors. What is the coefficient? If x is the coefficient, what is the vector here?
1 comma 3 comma 0.
And if z is the coefficient?
0 comma 0 comma 1.
Okay. So now we have a basis. Right? Once we have a basis, so these two are the basis vectors. So let's say v1 and v2. So we are now going to take any random vector x comma y comma z, and we find inner product v1 0 and inner product v2 0. Can you all do this and tell me what is your resulting value equations for xyz. From the first one, what is the equation for xyz?
X plus 3y plus z equals to 0.
Come on.
Plus 0.
Plus 0. Okay.
Okay. What about the second one?
It is
Z
z
equal to
equals to
0.
0.
So you have z is equal to 0. Okay. Now, what is your W perp? W perp is set of all x comma y comma z such that x plus 3y equal to 0 and z is equal to 0. This means you have x and then instead of y you can have, or maybe we'll write the other way around for easier purpose. So we can write x as minus 3y, right? And then here y, and then this is 0, y in R. So what can be a basis for this?
minus 3 comma 1 comma 0.
Okay, so in this scenario, what is the dimension of W?
2
What is the dimension of W perp?
1.
So you can see that dimension of W plus dimension of W perp is R3. Okay, fine. So finding the orthogonal complement, is it clear for everyone? Any doubts in this?
Clear, ma'am.
Good. So in that case, can I leave this as a homework, the third one? What is the procedure? You need to find a basis for this. From the basis, you just take any random vector and then take the inner product, and then you figure out from the equation what is the W perp. Okay. So I will give the third one as a homework. Fine. All right. So next we are moving to least square solutions. How orthogonal complements come into play here, and how are we going to use projections also. Okay, what are projections and how to use them. Fine. So we are going back to the very beginning, system of linear equations. Okay, everything is actually for system of linear equation, in fact, right? From the beginning we are seeing we started with system of linear equation, right? So rank, linear dependence, right, null space, everything is somehow finally going to system of linear equations, right? All these concepts somehow helps us in solving system of linear equations. Okay, now we have ax is equal to b. Okay, so we know that there are three possibilities: either the system have a unique solution, or it has infinitely many solution, or it has no solution, right? So these are the three possible scenarios. Now, any question? Okay. So what do we know? We know that. So for example, here, take this example here. Now, whether 1 comma 2 comma 2, whether this belongs to the column space of A. What is the column space of A?
Span of 1, 1, 1, 0, 1, 2.
1 1 1 0 1 2. So any vector in the column space is of the form, can we say, A comma A plus B comma A plus 2B, right? It should be of this form. Does 1 comma 2 comma 2 belong to this set? Okay, so instead of B, maybe I will give some other name because it may be confusing. Maybe I'll write C, because here also A, B is coming. So I'll write C. Does this vector C belong to the column space of A? How can you find? So here you see that 1 comma 2 comma 2. If I want to write it as A comma A plus B comma A plus 2B, what do I get? A is equal to 1, A plus B equal to 2. And then A plus 2B also is equal to 2. So from here, I get A is equal to 1, so B is equal to also 1. So, but here I get 2B is equal to 1, B equal to 1 by 2. So 1 not equal to 1 by 2, so we get a contradiction. If this means what? This C does not belong to the column space of A. If this does not belong to the column space of A, can we have a solution for Ax equal to C? Can we have a solution for Ax equal to C?
No, ma'am.
That is a main condition for existence of a solution, right? So for the solution to exist, the right hand side should be in the column space of the matrix given here. Okay, so in this case, you can also verify by writing down the equation Ax is equal to C has no solution. Okay, what can we do if it has no solution? Okay, what can we do if if there is no solution? In that case, we want to have some approximate solution. We try to have some approximate solution. Okay, what is mean by this approximate solution? That is what we are going to see here. Okay, so to find the approximate solution, what is the concept we are going to use here? Okay, here this is your Fm, right? Here A is your matrix. This is an M cross N matrix. If this is M cross N, what is the domain and what is the range? This is an M cross N matrix. So your A, what is the domain and range? A or T? What is the domain? For M cross N matrix, what is the domain? The corresponding transformation. Come on. Let's say you have a transformation corresponding to A. The domain should be Rm. Domain is Rm or Rn, Shanali.
Rn.
Right? It's Rn. So Rn to Rm. Okay. So you have Rn to Rm. So here you see this is the codomain. So your column space is inside your codomain. Okay, and you know that the solution exists if your vector B is within the column space, and if it is outside the column space, it does not exist. Okay, now how are we going to approximate if there is no solution? We will try to find a vector which is closest vector in column space. We find that and approximate with this solution. Find a x such that Ax is close to B. This is what we are trying to do. But how to do this? The logic is very easy. You all know the logic very well. What is the logic? If I ask you in some other way, you will give me the answer. Okay. So let's say that you are having some line here. Okay. And here you are here somewhere. You are here somewhere. What is the point on this line which is closest to this point?
The perpendicular line to it.
Exactly. So you just draw the perpendicular. This point is the closest to this point on the line, right? So let's say this point is P and this line is L, right? So the point on L which is closest to P is the perpendicular from P to L, correct? So this is clear for everyone, right? This is something you all know, right? Okay. So in that case, so can you in general now try to say that, so if you want to find what is the element which is closest, then what is that we need to find? We need to use some orthogonality, right? So you get some idea, but it may be very vague. Okay, but you have some idea that orthogonality is going to give us some solution. Let's see how. Okay, so distance from a point, distance of a point from a line. This is the thing which I just told you. So let's say you have a vector v, okay, and you have some line s. Okay, so this is your line s, okay, which is span of the vector u. What is the foot of the perpendicular v on the line s? So what is w star? So let's call the foot of the perpendicular of v on s as w star. How can we find w star? W star is simply the minimum of norm of v minus w, where w is in s. It means what? You take every single vector from this line s. You find the distance between that vector and v. Okay, the minimum of that is your w star, the vector which has the minimum distance between v and this line is w star. You understand what is w star? You are taking the distance between every single vector on the line with w, sorry, with v. The one which gives the smallest distance is your w star. Okay, and that is the foot of the perpendicular of v on s. So what is dv comma s? It is the norm of v minus w star. The distance between v and s is norm of v minus s star. Okay, so now how to find w star? How to find w star? How to find w star? We know that w star is simply inner
We'll
product.
take inner product.
Yes, that's all. Right, we take the normalized form of this u perpendicular u is u by norm u. So this is the normalized form of the vector u. Okay, and what is w star? It is inner product v comma u perp into u perp. We are projecting v on to this line. Okay, so this w star is the foot of this perpendicular v comma u perp u into u. Okay, so note that v minus u star is perpendicular to u, right? This is perpendicular to u. Okay, so the foot of the perpendicular is given by this formula here. Okay, now we know that how to find w star if you have a line and a point. How to generalize this? How to generalize this? Okay, so here what we did, we have a basis element, we then made it a normal vector, and then we found this. So in general, you can have a bigger space. In that case, you have a basis, right? You have a basis, then you know how to convert it into an orthonormal basis. Okay, so once you have an orthonormal basis, the projection of v onto s is given by the formula here. Okay, so you have the formula for w star in case of a bigger set s is here. Okay, so projection of v onto s. This is the projection of v onto s. Okay, and v minus w star is perpendicular to ui. The same v minus w star, the same thing we are having here for all the basis elements. Okay, and this w star is unique. Okay, you may feel that this formula, so many things are there, it's going to be difficult, but don't worry, once we solve some problems you will find it very easy. Don't think that it's going to be difficult. We solve few problems and you are going to find them very easy. Okay, fine. So if b is not in the column space of a, then we need to find a vector in the column space, say ax star, which is closest to b. So how are we going to do? We are going to project b onto the column space of A, and hence b minus ax star is orthogonal to the column space of A. Okay. So here you have Ax is equal to B. Here what is the columns span for the column space for A? So you take the columns itself, W1, W2, Wn be the span for the column space. Okay. Now we know that B minus Ax star is orthogonal to Wi because Ax star is the W star for us. What is W star here? This is W star. So B minus W star is orthogonal to every single element here. Okay. So here note that inner product B minus Ax star comma Wi is equal to 0. We can rewrite it in this way. Right? We can rewrite it in this way. The inner product can be rewritten in this way. If we are, this one you have already seen, right? Rewriting this in this way. Have you seen or not? So this is nothing but those who find it strange. There is nothing strange here. So this is something very well known to you. So let's say you have, for example, something like x1 comma y1 comma z1. Okay, inner product with, or you inner product with x2 y2 z2. What is the answer? We know that it is x1 x2 plus y1 y2 plus z2 z1 z2. Right? So now if we consider them as matrices, right? So this is now a 1 cross 3 matrix. This is also an 1 cross 3 matrix, right? So now I want to write this as, let's say this is 1 cross 3. So you have x2 y2 z2. If you want to write them, usually this we don't say 1 cross c, so the representation, I'll write the correct representation, otherwise it will be confusing. Okay, so you write x1 y1 z1. This is a vector. And what is the size of this vector? What is the order of this vector if you consider them as a matrix? It is
3 cross 1.
3 cross 1. Okay. Now, if we are writing them for general Fn, remember there is a conjugate. Okay, remember that there is a conjugate. Now, what is the conjugate transpose of the second vector x2, y2, z2? Conjugate transpose is given by h. This you know, right? The conjugate transpose. So this means that x2, y2, z2 bar, whole bar, and then a transpose. Right? So it means what? You get x2 bar, y2 bar, z2 bar, and then when you do the transpose, what will you get? x2 bar, y2 bar, z2 bar. The column will become a row. Okay. Now, what is, so let's say this is u, this is v. Okay. So now this is your u, this is your vh. What is vh into u? What is vh into u? x2 bar, y2 bar, z2 bar into x1, y1, z1. Now this is a 1 cross 3 matrix. This is a 3 cross 1 matrix. So what is the resulting element? x1, x2 bar plus y1, y2 bar plus z1, z2 bar. Okay. So you can see that inner product u comma v is same as vh into u. Is this representation clear for everyone? Yes? Is this representation clear for everyone?
Clear, ma'am.
Okay, good. Sanand, you have asked something extra. I don't know where you were asking. You are asking about why we are getting an X star here. Is this what you are asking? Instead of a W star, why are we having an X star?
Yes, ma'am.
See, here, any element in the column space is of the form AX. Yes or no?
Yes, ma'am.
Any element in column space of A is of the form AX. Okay. Now W star belongs to column space of A. So there exists X star in Fn such that Ax star equal to W star, correct? You got it now? Okay, instead of W star,
Yes,
I
ma'am,
can
got it.
represent the answer in terms of X star also. Okay, fine. Okay, so now I guess this part is clear that you have now inner product B minus Ax star into Wi equal to 0, which can be rewritten like this. Okay, after rewriting, we are just splitting the terms. Okay, we are splitting the terms. So you have WIHB minus WIHAX star equal to 0, which implies this. So I'm just bringing one term to the other side. So you get this. Okay, so you have W1H, W2H, WNH. This is your WIH. This is what? This is your WIH. And what is this? This is your AH. Okay, so each of this column is your WIH. Okay, so it means this is your simply AH and this is your AX star. So you have AH into B. What is that happening here? What is that happening here? WIHAX star equal to WIB. So I am now writing it for each I. When I write it for each I, what is that I am getting? I am getting that AHAX star is equal to AHB. On the right side, I get AHB, and on the left side, I get AX star. So this, when I am applying for all i's, I get this expression. So what has happened, I will just quickly recall. We are trying to find the solution for Ax is equal to B. This is what we are trying to find. So when there is no solution for this, then what are we trying to do? We are trying to find an approximate solution. Find approximate solution. How are we finding the approximate solution? We are going to take the vector B minus Ax star, which is perpendicular to the column space of A. So we are projecting the vector B onto the column space. Projecting B onto column space of A. Okay. So that is projection is your B minus Ax star. So since it is a projection, what is projecting means? Do you understand? I sorry, I have not used the word projection earlier and I'm suddenly using here. So it means what? So let's say you are in R2. Okay. And this is some point, let's say it's 2, 3. What is the projection of 2, 3 on x-axis? Projections means the perpendicular. So what is the projection of 2, 3 on x-axis? Can you say? What is this point?
W star.
No. What is this exactly?
2, 0.
Exactly. So this 2, 0 is the projection of 2, 3 on x-axis. Same way, what is the projection of 2, 3 on y-axis?
0, 3.
0, 3. Now suppose I am having some line here. What is the projection of 2, 3 on this line? What is this point? That is given by this formula. Okay, inner product V, U hat into U hat. Okay, so that's why the name projection of B onto column space of A I am giving. So earlier I am just telling the perpendicular line, the perpendicular distance, but that is nothing but the projection. Okay, the terminology we are using to call the foot of the perpendicular is the projection. Okay, projection is just a word for the foot of the perpendicular, we can say. Okay, fine.
Ma'am, please do an example.
Yes, we are going to do now. Okay, so now you have AH star equal to AHB. From this expansion, you rewrite them and you get it this. You get like this. Now, instead of solving AX is equal to B, what I am going to do? I am going to solve AH star equal to AHB. Okay. Now, I am going to have some examples here Okay. Now, first of all, whether they will have a solution or not, you have to tell. Will they have a solution? If this is A and this is B, whether Ax equal to B will have a solution. Whether 1 comma 1 is in the column space of this matrix. Here the column space, the basis is very obvious here. Can anyone say what is the basis for this? Some basis? These two are, what do you observe from the two columns? The second column is multiple of the first column. It means it is just span of
1, 2.
yes.
1 comma 2.
All right. So this is just the column space span of one single vector. And now whether 1 comma 1 belongs to this span?
No.
No. Right? 1 comma 1 is definitely not of the form 1 comma 2, right? So this is definitely not there. So in that case, we have to now look at what is AX star into AHB. Okay. So in the case of real matrices, AH is same as A transpose. If A is a real matrix, then AH is same as A transpose. So for the first problem, what is AH? Can you tell?
1, 2, 2, 4.
It's the same matrix in fact. Right? Now compute what is AH into A. Do the matrix multiplication and tell me. Yeah.
5, 10, 10, 20.
5, 10, 10, 20. Okay, fine. What about B? Sorry, AHB? 1, 2, 2, 4 into B, 1, 1.
Three, 6.
Okay, so now AH, let's say x1 star, x2 star equal to 3, 6. This gives you 5x1 star plus 10x2 star equal to 3, and then 10x1 star plus 20x2 star equal to 6. So both this equation, the second equation is just multiple of the first. So you can just take the first equation, you have infinitely many solutions, right? So the least square solution are all x1, x2 star, or just simply x1 satisfying 5x1 plus 10x2 equal to 3. All this vectors satisfying this condition are the least square solution. Okay, fine. So how to find the least square solution is very easy, right? You simply have to find AH, then find AHA and AHB, solve AX equal to AHB. Just solve this equation, you will get the least square solution. See, there are so many gaps in between because there is too much theory involved. Like here, how did we get this formula? How did we get this formula first? Then how did we get this formula? And then here also you can see that, okay, we have this equation, there is no solution. Now why there is always a solution for this? Why should this equation always have a solution? Okay, and why the name least squares? So many gaps are in between. Okay, so those who are interested, there are several websites where you can see, or you can also have books where you can see this kind of problems and explanation for these things. If you want again some links, I have to just collect everything and give it to you. Okay, those who are interested to understand what's going on behind this. See, the word least square basically comes from the norm only. Okay, so here you have this norm, right? So in general, what is the distance between two vector? Euclidean norm, at least, what is the distance between two vectors? So let's say you have, this is x1 y1. If this is x1 y1 and this is x2 y2, what is the norm? What is this norm representing? Square root of
x1 minus x2 whole square plus y1 minus y2 whole square.
Okay, so here we are looking at least square solution, in the sense that we are trying to, now what we did here, we were looking at the distance between each of the vector on the line and this vector, and the one which has the least difference. Okay, the least difference, that is the one we took as a solution. So here we are taking the squares, okay, the sum of the squares and the least value of those, and that's why this is a least square solution. At least this was something quick I can tell, so I told this. Why the name least square? Do you get an idea? It comes from here. We are taking the sum of the squares and the least value of them, that's why the least square solution. Okay, fine. All right, Joe. So I just told you the reason for the name least squares. So will you be able to solve the similar problem here? Because I have some more things to cover. So if you can manage this problem, and if you have any issues, please ask Dipanshu. Tomorrow Dipanshu will be handling the session. For the second problem, this is something very easy. This is your A. You simply have to find A transpose and solve for A transpose A x star equal to A transpose B. Okay, this is nothing difficult, but if there is any doubts, you can, or if you want to verify the answer, you can do it in tomorrow's session. All right, so is that okay if I leave this problem?
Yes, ma'am.
Okay, fine. Okay, so what is a projection operator? Here we are not going to see anything new, but whatever we have seen earlier, we are going to kind of put them together. Okay, the projector operator from Fn onto S, denoted by Ps, is defined as the mapping from V to W star. So we have any vector. What is the projection of a vector onto a subspace we know, and now we are going to give it a name. So Ps denotes the projection of V onto W star. Okay, and this Ps is a linear operator. Okay, this Ps is a linear operator. It means what? Ps of V1 plus V2, if you take, it should be Ps of V1 plus Ps of V2. So here, for example, let's say W1 star is the projection of V1 onto S. Same way, W2 star is the projection of V2 onto S. Okay, now you know that V1 minus W1 star is in S-perp and V2 minus W2 star is in S-perp. These two are in S-perp. This is something we know from the definition, right? Now, what is PS of AV1 plus BV2? Okay, we want to show that it is equal to A times of PS of V1 plus B times of PV2. How can we do that? Here you have A times of V1 minus W1 star plus B times of V2 minus W2 star. Here you see it is AV1 plus BV2 minus AV1 star plus BW star. This means what? This is what you are having. So something similar to what you have here. Okay, this is the first part and this is the second part. So this means that, so let's say this is your U. So this is your projection of U. So PS of U is simply this vector here you are having. Okay, this is your U, the projection is this, because this belongs to S-perp. Okay, fine. So this is a linear operator. Now, okay, so here is something more before going to how to find PS. What is an orthonormal basis for S perp? This is something very easy. Here, let's say you have some basis for S, okay, and you know how to extend a basis to Fn. So let's say u1, u2, uk is a basis for S, and you are extending with some other vectors to Fn. Then this uk plus 1 ukn, they all are forming a basis for S perp, and this is if this is an orthonormal basis for Fn, then this is an orthonormal basis for S perp. So you can very easily see it from some example. Let me show it with an example, then it will be more clear. Take this one. Okay, so now for example here 1 1 1 minus 1 0, this is a basis for S. Now we can extend the basis of this to a basis of R3 by including this vector here. Now this will form an orthogonal basis to R3. Then we can orthonormalize them in this way. So we have an orthonormal basis for R3, where this is an orthogonal basis for S. So this will form an orthonormal basis for S perp, that we already know, right? This is what they are saying in this theorem as well. Suppose you have a basis for S and you extend the basis to R3, then the extended part, the vectors which are added, will form a basis for the orthogonal complement. Okay, that is what they have mentioned here. Okay, fine. Now how are we going to find the projection? Okay, so let's say you have a basis, orthonormal basis for S, okay, and you are extending it to an orthonormal basis for Fn. Okay, how are we going to find the projection PS? Okay, for that it is very easy. You simply have to calculate this part. Okay, how we got this? Let's say you have any vector v in Fn. You know that you can write it as a linear combination of the basis element. And since they are orthonormal, what are the coefficients? Do you remember? The coefficients are simply v comma u1, v comma u2, v comma un. Right? So writing v as a linear combination of these elements with these coefficients. And then what? I'm going to apply the projection. When I apply the projection, what happens? What happens when I apply the projection? By the way, there is something which I really wanted to ask, but I forgot. The same example I will take. Okay, so you are here at 2 comma 3. When I project it onto x-axis, I got 2 comma 0. What is the projection of 2 comma 0 on x-axis?
0.
0. 0.
It's same.
Itself, right? So it's already here. I want to project it again on the same line. So it's going to be the same. Yes or no? Right? Projection of
Yes, ma'am.
2 comma 3 on x-axis is 2 comma 0. Right? Now 2 comma 0 belongs to x-axis. And now again I want to project 2 comma 0 on x-axis, which will simply give me 2 comma 0. Okay. Now what is the projection of 2 comma 0 on y-axis? What is the projection of this on y-axis? This side you have to see. This is your y-axis. When it gets
0,
projected
0.
here,
0, comma 0.
Yes, right? So what are the two observations you see here? The two observations are that projecting a vector from S onto S. You take any vector from S and project onto S, so it will be same. Okay, so projecting a vector from S perp onto S. Can you give the answer? We just saw. So if you x-axis, suppose x-axis, y-axis is your S, then x-axis is your S perp, right? So I took some vector from S perp and projected it onto S. Then what happened? I got the 0 vector. So same way, projection of a vector from S perp onto S will give me
0.
0 vector. So these two are some observations we have. There is another observation again from the same thing. So P of 2 comma 0 is equal to 2 comma 0. But 2 comma 0 is P of 2 comma 3. Right? P of 2 comma 3 is P of 2 comma 0. Right? And here you have this is P 2 comma 0. Okay, so what is happening here? Oh, sorry, not P of 2 comma 0, simply 2 comma 0. So what is happening here, or in general I should say for 2 comma 0, what is P of 2 comma 0?
0.
No, just now we
2
said
comma
that
0, ma'am.
2 comma 0, right? So there is some relation between P square and P, that also we will see. So these are some observations which I wanted to make before moving on. Okay, so from these observations, whatever we have seen here, see now this part here, the first part, they are from S, and the second part, they are from S perp, right? So when we are doing the projection of the part of S onto S, then only this will remain and this part will become 0. Okay, so when we are projecting any vector, the part of S will remain and the part of S perp will go away. That will vanish. This part will become 0. Okay, because these are all vectors in S perp. We are applying this concept we saw here. Okay, so one way we are left with this part. Now in this part, we are doing some rearrangement as we did earlier. Instead of V comma U1, I'm writing it as U1H, U1V into U1. Okay, and I'm rearranging the entire thing. So now I'm taking the scalar here, again doing some rearrangement, taking V commonly. Finally you get this particular entry here, which is the matrix of PS with respect to the canonical basis. So how do you find PS? You take the orthonormal basis for S and then you calculate this. That will give you the matrix of PS. Okay, so what are the properties for PS we saw? If U in S, then PSU equal to U. Okay, and if W is in S perp, then PS of W equal to 0. And what is range of PS? It is equal to S. It means what? You take any element from the space from R2. Okay, when you do the projection, it is always going to fall on the same S. Okay, suppose you are projecting any vector onto x-axis, then all the vectors all are going to be on x-axis. So x-axis is going to be your range. If S is the set you are considering for projecting, then that is your range. Okay, so the projection, the range of PS is yes. Is this clear? Because this is something very important. If you want to understand projection, then this should be clear. Is it clear why range of PS equal to S? Yes or no? No?
Yes, ma'am.
Okay, good. And null of PS is S perp. Why null of PS is S perp? Null is all the vectors which are mapped to 0. You see that for any vector in S perp, they are mapped to 0. So the null is nothing but S perp. So range is S and null is S perp. And PS square is equal to P. Right? Why is PS square equal to P? What happens? You take any vector V in S, sorry, V in Fn, and what will happen? You know that V can be written some part in S and some part in S perp. So let's say this part is V1 and this part is V2. Okay, then what will happen? What is P of V? P of V is, what is P of V? It is simply V1, right? Now what is P square of P of V? not p square of p of v, p of v, p square v. That is p of v1. But what is p of v1? Can anyone tell what is p of v1? Projection of v1 onto S. Come on, its answer is here. v1 is an element of S. What is the projection of v1 onto S?
V1.
v1. Okay, so what is that we notice? PS of v is same as PS square of v for any v. So in general, you have PS square equal to PS. Okay, so all these 5 properties are very important for a projection operator. Okay, so here there are few problems. Find orthonormal basis and projection operators for the following subspaces. So here finding orthonormal basis, you know, we have to use Gram-Schmidt. Once you have, let's say, so for this, let's say this is your V1, V2. Okay, so what is the step 1? This is the third problem. So step 1, apply Gram-Schmidt. So once you apply Gram-Schmidt, we get U1, U2, which is an orthonormal basis for S. Okay, so this is your S. Okay, you get an orthonormal basis for S. And what is step 2? You find the matrix PS, which is, here you saw this formula, right? U1, U1H plus U2, U2H. That's all. Okay, these are the 2 steps. Everyone try to do the problem yourself because you already know how to apply Gram-Schmidt, and this is nothing but some simple calculation only. Again, these problems also I will tell Dipanshu to cover in tomorrow's session. Okay, so this and this is something very easy, but anyway, I will tell Dipanshu to cover these parts, the problem part, in tomorrow's session. With this, we are. See, week 10 is quite a lot, you might feel. Okay, fine. If there are any specific difficulties, please tell it ahead in the group to Dipanshu so that he will. So maybe you would say least square solution, problems for least square solution, or any particular topic you want in tomorrow's session. Please mention in the group chat so that Dipanshu will know what are the things he need to concentrate in tomorrow's session. Is that fine? Yes.
Yes, ma'am.
All right then. Any questions from today's session?
No, ma'am.
All right then. Thank you. See you again in some other session then. Thank you. Bye.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.